So, what am I going to be talking about, an outline? What I'm mostly wanting to get to are the last two bullet points you see up there about software engineering. So I will say up front that this may be a little bit different in spirit talk than some of the talks here, but I do think it's a strength of meetings like this that we get to have some different areas of expertise. So I will begin with an overview of gravitational wave data analysis computing to kind of establish some terminology. I know that's going to be very familiar to a lot of you in this room, with a particular focus on how it plays out into computing needs, how much computing you need, what kind of computing you need. And then I'm going to say a little bit about how those challenges will change as best we can anticipate now with third generation detectors. And then I'm going to take a little bit of a deep dive into some aspects of the hardware of computing that maybe are unfamiliar to some of you, and talk about the places in particular, some places where it doesn't pose a challenge for us if we do things correctly, and some other places where I do think we need to be ready in some possible ways to address this. So probably the closest thing to a publication that may address some of these things I'm talking about is the computing report from the 3G subcommittee of GWIC, which I was participated in writing. So it's a little unusual, but also a little bit about me and who I am and why I'm here speaking to you right now. I'm currently a staff computational scientist with the LIGO project, Caltech. I don't actually live in California, but Texas. And I support both laboratory computing and in particular LSC scientific computing. So I have worked on both grid computing, so some of the pieces of the infrastructure that our analyses use in order to run, particularly so that you don't just run at one particular site, but at many sites throughout the world. I'll say a little bit about that. And I've also been heavily involved with optimization, so improving the performance of our analysis code so that the overall computing usage is less and hopefully things like time to solution are less. I may make some references to having taught a class once because I did used to be a faculty member at a teaching university, and I joined LIGO in 2011, and I, in the distant past, have a background in classical and quantum general relativity. So, some background on gravitational wave data analysis. You've probably seen some version of this slide, including some with prettier pictures than I've dug up for you. There's a few different ways you can break it down. In the computing group, we're often wanting to look at the collective whole. So what is the overall computing? And we'll focus on our biggest users of computing. That's not because that's the only thing that matters, but when you're targeting both supply and demand, we get the best return for investment at that. So if you look at searches, then you can break it down both by what kind of signal a particular search is looking for, what the source of it is, and some characteristics about how you're doing the search or about the source itself. So you've heard already yesterday about continuous wave sources. So what the characteristic here is simply that the signal persists essentially for the entirety of your observation period. There are some variations on that, but to a first order, you can think of it that way. And so that's one category of source, so either isolated pulsars or pulsars in a binary system where you're looking for the gravitational wave generated by an individual pulsar is the canonical example of that. Compact binaries, and here's where the different ways of dividing things can show up. So internally, within the LIGO and Virgo and Kagra now collaborations, we'll have these working groups dedicated to different types of sources. And so there's a burst working group and a CBC working group, compact binary coalescence. But both of those groups can see this category of source, particularly at the high mass end of things. But often for computing purposes, it does matter what the technique that's being used to find it. So these are, whichever technique you're talking about, transient signals in this setting. So in our current second generation detectors, these will be in the sensitive band of the detectors for fractions of a second at the shortest, up to a few minutes for the lowest mass systems. But you can look for them either using match filtering, where you are putting in some input of what general relativity or even an alternate theory of gravity predicts for what the signal should be, or you heard, for instance, Marco yesterday talking about burst sources, in which you're using unmodeled. And of course, those unmodeled searches, so you see burst there at the very end, can search for more besides compact binaries using the same techniques. That's one of the strengths of those kind of sources. You don't have as precise of a model necessarily, but you make fewer assumptions, so you're sensitive to things that may look differently. And then stochastic, the background of signals, which I won't say as much about because principally right now, it just isn't a big demand on our computing. So my definition on the previous page was for searches, kind of the character, what makes a search from other kinds of data analysis is you'll look at all the data at some point, or almost all of the data. So you're trying to find whichever category of source you're talking about within the data, and importantly, you're trying to estimate the significance of that data. A lot of our searches would be computationally much more feasible if it were a true assumption that we were in perfectly Gaussian noise, but we very much are not. And so you've already heard many talks this week, and you will hear more about how we have to mitigate that, and that's one of the chief complexities of match filter searches. However, that's not the only kind of data analysis, broadly speaking, that our collaborations engage in. Once you find things, which so far has been in the compact binary coalescence case, then you want to do follow-up computing, and the computational needs here can themselves be fairly intense. So collectively, the first level is for one candidate signal. I try to infer its properties. We just normally refer to as parameter estimation. I know many of you in this room are experts on that, more experts than me. And then, of course, if you have a collection of candidates, then it's also interesting to look at what you can infer about the populations of these. And collectively, this can require a very significant amount of computing. Let me say a little bit more about matched filtering. Partly where I'm headed here is to try and lay some groundwork so we understand what kinds of computing we need when we're trying to look at the whole scope of this computing. So when you have a good model of the source, which can happen, for instance, for either compact binary coalescences or isolated pulsars. Now, you may have to make some assumptions about the values of the parameters. Then the optimal statistically search technique to use is some variation of match filtering. I say some variation because you can improve if you have models of the noise, if you have models of the signal population, you can sort of show that the optimal statistics take that into account. And most of our search techniques do try to fold those in one way or another. And then I also say not necessarily computationally optimal. So throughout this long program and also this week, you'll be hearing about other techniques that do not consist of simply looking at a range of parameter space and all of the sources there. But you compare each stretch of data to your candidate signal, and then you have some parameter space of those candidate signals. Now, for continuous wave signals, the ideal thing you would like to be able to do, the stretch of data would be all of the data that you have, essentially. But an exhaustive search, match filter search, is just computationally intractable. So all of the production searches that are currently done look at shorter stretches of data and then combine the results of those in some method. For transient searches, the classical canonical CBC searches, this approach is feasible, and that's basically what all of our production pipelines for what we would call CBC, meaning a modeled search, have done. And again, also, many of these same signals are visible to burst searches that are not making a match filtering assumption. So the terminology we use is that this set of templates is a bank, and you're just going to compare your stretch of data against each template in the bank. And you choose the templates in the bank so that they're close together in signal space. That is how they look. Usually, a common choice is to say you don't lose any more than 3% of signal-to-noise ratio going from one point to the next, which would correspond to possibly a 10% loss in sensitive volume. You can make different choices. Now, for the signals that we're talking about in second-generation detectors, these can be up to a few hundred seconds long for the very lowest mass systems that we've searched for binary neutron star larger. Now, there are people who, for instance, have looked at subsolar mass searches. The full parameter space of a canonical binary system, which has a spin for each component and a mass for each component, and then which are intrinsic parameters, which are often what are astrophysically most interesting to us, combined with where is that source in the sky, and how is it oriented relative to us? If you just do that counting, then you have a 15-dimensional space that you might, in principle, think you have to lay templates out over to search. And yet it can be higher if you also want to include model matter effects, if you think there's a neutron star in there, or other effects. In practice, our searches don't look at a space nearly that high dimensional. So thus far, it has always been sufficient to look at 2.x dimensional searches. So I have here from an 01 paper, one of the template banks where the color that you're seeing corresponds to the spin range that's allowed for the aligned spin component. So we only look at aligned spin component, take those 3 components of 2 spins and just reduce it down to 1 effective component. And then we're looking at the masses of each component. And that's sufficient for the intrinsic parameters, and then for as long as we do what we call a coincidence search, which is we do the match filtering in each detector separately, and then just look at significant signals there, then it turns out that for the simplest waveforms, where you're only looking at the 2-2 mode, you can analytically maximize over some of these other parameters, so that reduces the dimensionality for your parameter space, and that's important computationally. If you had to lay out a grid in some of these other dimensions, it would really matter a lot. And I say 2.x because you don't have to cover so much in this aligned spin component as you might theoretically think. That's for searches. For parameter estimation, things are different. So as we've found more and more things, and as we've seen possible hints of evidence of more and more physical effects, we have to increase, start approaching that full dimensionality of the parameter space. We do have to look for, do we see evidence of precession in higher order modes? And certainly, even if you're using simple aligned spin models to do your parameter estimation, you really do have to look over all of these extrinsic parameters, the 8-dimensional space of when did the signal happen, what was its initial phase, how is it tilted relative to us, the polarization, all of those components. And so right now, the methods that are principally used for this in our production searches do some different kinds of sampling algorithms. So you can either do Markov chain Monte Carlo, which is the classical approach used in lateral inference with some very particular customizations to make it sample more efficiently. There's also nested sampling. And so you have to explore this full space. You have to do that basically now. So there's really no question that we'll have to do that for 3G detectors, which will be much more sensitive. To a very rough order of magnitude, if you look at the computing usage thus far that we've had, and we will analyze any given signal sometimes a few different ways using, for instance, different models of the waveform for waveform systematics. We're spinning at about 1 million CPU core hours for each of our events. So right now we've had about 90. That's a bit of a hand-wavy estimate. I stole that number from at the very beginning of this long program. Peter Kovaras was giving an introductory talk. So I don't intend that to be very precise, and there are some other things that come into play there, other uses of that code. But you should kind of have that in mind as what a benchmark is. So that's a lot. It's not an unobtainable amount of computing, obviously not unobtainable since we've done it, but you need to sort of have that in your mind of what happens if I look to the future to third-generation gravitational wave detectors. Now let's say a little bit about, and again, some of this will be repeating some things that Peter talked about, but I know that's a while ago and not everyone here was here for the whole program. And so I want us to have sort of a common framework. And what's important to me to say here is to understand something about the way we can do this computing. Because there are actually some advantages to some of our computational tasks compared to other things that some people work on. In particular, one that may be very familiar to many of you here compared to numerical relativity. So matched filtering, when that's what you're doing, is what we would call embarrassingly parallel. I can look at different parts of the template bank. I can split it up to as many pieces as I find I need to, and then look at different chunks of the data. I can't cut it down arbitrarily small because I do need to estimate a power spectral strain density over a reasonable stretch of data for most of our techniques. But those individual jobs in a workflow don't have to talk to each other. So if I've got a core that's off doing that computation, another one can be somewhere else doing it, and it's only at the end that we take these significant candidates in each detector and start bringing them together. So a relatively tiny fraction of the jobs in the workflow that actually bring all of the knowledge together and do this estimation of sensitivity. So that's an example of what in computing we call high throughput computing. It's an overall large use of computing, but I don't have to have inter-process communication between many different of my jobs. I might have a couple, they might happen to be at the same place. That's in contrast to fluid dynamics simulations. If you were working on climate modeling, and again, as I said, numerical relativity, where you need to have one cluster where not only have they spent a lot of money on the CPU cores, or GPU, if that's what you use, but also the interconnect, the networking between them, because that's generally your limiting factor in computation. The sampling methods for parameter estimation that I've alluded to, don't fit quite so nicely always into that model. There's some parallelization you can do because they'll often, internally, they may talk about temperatures if you're doing sampling, and so some of those can be done a little bit independently for each other. The primary parallelization is going to be I may analyze the same event more than once and combine the samples from those. And then, of course, there are many, many events. And what I analyze on one event doesn't require the results from another. But those tend to be long-running jobs. Some of them can take up to weeks to complete. And it's very serial in nature. The one sort of exception to this is there are some variants of the nested sampling. And I think you will have heard about this will have been presented already earlier in this conference, which can parallelize a bit. But that's in the high performance computing. So to computing professionals, the HTC, high throughput computing, has the advantage that all of the computing you do, you don't have to talk to each other for a while. Whereas HPC, it really needs to run on one cluster, at least right now. And we do have some examples of that. So summarizing in one or two slides, something that Peter spent a while talking about, and there will be a talk this Friday by Frank Werthwein, who's the director of the Open Science Grid, about some of that infrastructure. And again, this may be very familiar to some of you, or you may have used it. You may have not necessarily thought about when interacting with a terminal what's going on behind the scenes. But for high throughput computing, the strength is that my jobs don't have to talk to each other, but I still got to organize them. And that's a pretty non-trivial task. But it's also a fairly generic task. And so we've had great success by using software developed by groups that are really dedicated to facilitating this. And in particular, for most of these workflows, if a particular analysis job may run for an hour or two, or in the case of a parameter estimation job that may run for weeks, it may run for a while at one location, save its state, and migrate to another one, because typically at these clusters, you're not allowed to just occupy a given computing core indefinitely. So we've been using the Open Science Grid, which allows us to connect to both our own resources that are owned both by the laboratories themselves, LIGO, and affiliated LSC institutions. In the case of Virgo, it's fairly unusual for those clusters, for them to have their own clusters. Instead, they are allocated time proportional to their needs on some national or European-wide computing clusters, so we have to be able to access those resources. And then there are times when we can use computing resources at things that logically have nothing in particular to do with gravitational waves, but scientific computing, because there's often common funding agencies, for one thing, behind a lot of these, would much rather a core not sit idle. So this infrastructure allows us to kind of come in and run there when we need to, even if that's not the dedicated purpose of that cluster. So for instance, high energy physics has a lot of these clusters that are plumbed into the Open Science Grid. There's also issues with moving the data itself around, which is non-trivial. Part of when I'm working with people on porting an analysis pipeline to run, the most common assumption that we have to address is I can't just write to my file like it's right there and then read from it later by another job. It has to be physically moved around throughout the world. These things, one workflow may scatter and run at many different places on the world. And then the input data, which can be large enough, can require some significant infrastructure. I'm not going to talk in detail about that. There are also some other input files that will be needed. I'll say a little bit about one of those kind of files here in a bit. But that's just sort of the background. And the main takeaway here is high throughput computing has the advantage that the jobs don't have to talk to each other, but they could be running at lots of different places. And that'll be important here in a bit. So far, we've detected 90 binary mergers. I think that's current as of a week or so ago, that's all public. Planned 3G detectors could detect more binary mergers than that per day. So depending a little bit on where you think the sensitive noise, the lower end of that noise curve is, you could be looking at anywhere from of order 10,000 to almost 100,000 mergers in a year of continuous observing time. So if I took that number that I just said of 1 million core hours for merger, and I multiply that by 10 to the 4th or 10 to the 5th, I'm looking at a large amount of computing, right? 10 billion core hours in computing. Some of these things also have latency that can run, especially for PE and some of our production searches now, for the most sensitive PE that explores the parameter space most fully, can run for, as I said, up to weeks. We call it rapid PE right now if it delivers results just in a few hours. But if I'm looking forward to 3G detectors, then I need to do a lot better than that, because a lot of the good science that I can do, and if you look at the science case studies that are written about what can I do with this, they don't assume that I have to wait that long to get an answer. Certainly if I want to do triggering on electromagnetic counterpart test, but also in terms of parameter estimation, some of the more interesting things you can do to do population studies. I need precise estimation of parameters from a large category of these events. And if you can imagine that 3G it will be a more sensitive test of general relativity. So I need to have high confidence in both my models of my waveform and the accuracy of my sampling, so that if I think I see evidence of any deviation from general relativity, for instance, that I can be confident in that. It's not an artifact of not having a converged sampling run. And we try to balance optimism about new techniques, which we're exploring at this conference and then this entire long program. I will say that my experience being on the computing side in 2G is anytime something is unexpected, what we do is we analyze it a lot more with several things. So it is always good to have in mind your best case scenario of what your computing needs are, but it's also wise, thus far at least, to expect that that could be significantly higher and to plan for that availability. One thing to mention, because if you haven't worked on these a lot, it may not be obvious that the match filtering is actually most sensitive to the shape of the PSD. So I will try and use my pointer here. So if you're on Zoom, I'm looking at this figure off to the right, which comes from the the R&D document from the GWIC site that I mentioned. So up here at the top in blue, we see advanced LIGO, and then we see a couple of different proposals for a Cosmic Explorer and for the Einstein telescope. Of course, why they're so much more sensitive and let us see things we can't see is that they're so much lower on this plot versus frequency. But what actually makes a lot of our match filtering more challenging, depending on which kind of match filtering, whether I'm looking for transients or longer sources, is how much they're moved either to the right or to the left. So if I'm looking at a transient source, it's going to stay in the sensitive band of the detector much longer because of this low frequency cutoff. So my signals won't be seconds to minutes long. They might be minutes to almost a day long, certainly hours. And then if I'm looking at I'm not the expert here, but if I'm looking at CW sources, it's more that I will be sensitive to higher frequencies, and the higher and higher frequencies are the more and more demanding continuous wave sources. So in particular, even this small difference here between Einstein telescope and Cosmic Explorer can still correspond to a reasonably significant difference in what sort of template bank size, again, if I take what I know, what we do right now, and extrapolate that to 3G. However, having said all that, even though the signals are longer for matched filtering, the searches, again, what will look at all of the data and tell me, which of the many seconds of the day, which of them have something in it, there's an increase. But, for instance, one paper here by some folks at Syracuse predicts it's more like a factor of 3, even allowing for some eccentricity. Again, I don't want to say that that's the only possible answer, but it's not an orders of magnitude increase in the size of the template bank. It's increased, but not enormously so. This is assuming that you don't find scientific reasons that you need to increase the dimension of your parameter space. So in particular, this means I'm still doing a search in which I am looking at a line spin for the search, and therefore I have this relatively low dimensional template bank. If I needed to do some kind of search that looked for processing signals, so in particular those will often look fairly different in different detectors, then that computational cost could start to increase more significantly. Right now we don't really have searches that efficiently do that. We haven't used them in production, but that doesn't mean they might not be interesting for 3G. However, what's more important often is to find things at all, and then you can still come back to something that may well have precession or these other effects. But if you found it, then you can still run an analysis on it with parameter estimation, even if that wasn't an assumption of your search used in looking for it. And in that case, you're actually helped by the fact that things are just louder. So they're just generically often easier to find, even out to some of the edges of the earliest universe. Continuous wave searches are, as I said, if you actually run the numbers for what would a match filter search look for right now, it's many orders of magnitude more than all the computers in the world, and that remains true. So that's still intractable, and so we'll still need sophisticated techniques to deal with that. However, the more challenging problem, and let me try and step back into the light here, is likely to be parameter estimation. So if I just took what we do now, where I do these sampling methods. So at each sampling method, I generate a template according to all of those parameters, including those intrinsic parameters, more of the dimensionality of the parameter space than I looked for in the search, because I'm trying to really explore that and come up with an answer that's not just a number, but tells me something about the distribution of how confident I can be of what parameters this source might be. Then even the simple thing we already said is a huge amount of computing, and that's assuming that it stayed that simple. It won't be, because those signals, those templates will get much, much longer. So in parameter estimation, you're actually dominated, if you profile the code, by the cost of generating one of these waveform templates. And then it's a relatively simple operation to convolve that at one choice of parameters with your data, and that tells you what your likelihood is. And then based on whatever sampling technique you're using, you make decisions about how to explore other points in parameter space. If you just naively took that into account, you would find this is an intractable problem. Like it's just not feasible. But that's not what people are really proposing. So when people are writing science case studies for 3G detectors, we're not assuming that we're going to do all of that. So let me highlight a couple of things here first, which are similar to what we do now in production searches, and in some cases have been used in some of our production searches. That is, they are still doing sampling a parameter space. It could be MCMC or nested. But they are still moving around, walking around through sampling space with the end goal of coming up with a sample of points that are representative of the distribution, but are ways of speeding that up from an algorithmic perspective. So the Princeton group first proposed this relative binning technique in this paper and demonstrated it on GW 170817, where in that particular case, it's very well adapted to that particular way of looking at it. So this basically takes a reference waveform and computes the change in your likelihood as you stay near that. I'm not going into the details of this just because I want to sort of highlight that we have techniques, but they all still involve evaluating the waveform. Then another one which we have used is reduced order quadrature. There are lots of citations I could have here. These last two are some of the earlier works, and we have used this. We're looking forward to using this in 04. This particular first citation is a large group of people. I don't remember if any of them are in this room, but if not, they probably have come through here, which actually demonstrated a feasible and of order, I think it was a day of computing on, I forget how many cores, but it was tractable for a binary neutron star in 3G. And so reduced order quadrature first computes a basis, and then you will evaluate the waveform, but only at a small subset of the frequency points out of all the possible ones that you might imagine you would have if you just did the brute force thing. And then throughout this long program, you have had people will have, and certainly this week, people will have talked about using machine learning. So that could be fairly different. That's not necessarily going to be a sampling technique and a straightforward approach. I'm, again, not the expert to talk to you about that. And I apologize. I was in transit for Deep's talk and had to step out for part of Michael's, but you heard some discussion of that and the use of that for sampling. Jonathan Gare is going to talk about that this Friday, I think, if I remember right. So these approaches would look pretty different. But all of them, to my knowledge, and again, I am happy for some of you experts to correct me a bit on some of this, will still need to generate the waveform at some point. Even the machine learning methods, they're very fast when they run, but they do have to be trained typically with waveform samples. So that's like what you're giving your neural network if you're using a neural network in order to teach it to distinguish these samples. And again, some of the early machine learning results are encouraging, but if we're thinking ahead to 3G and the high level of accuracy that I need to obtain, we need to, I think, be prepared for our training of even machine learning methods to possibly be significantly more expensive. Partly that's generically what is found with machine learning, that the things that make all the news about computers beating humans in Go, what the expense of that is in training the neural network. You will hear a talk on Wednesday on actually generating the waveform with machine learning by Layla. But the bottom line here that different authors can talk about, but I've cited this preprint from Purer and Haster that for 3G, these waveform models will need to be much more accurate than they are right now. So possibly an order of magnitude for numerical relativity and several orders of magnitude for the analytic part. So the waveform models typically combine both of these. And so for the rest of this talk, this is where it's going to be maybe even more different than what you're usually hearing this meeting. I'm going to talk about some software engineering aspects of that. So let me jump back and talk about computing performance and what determines how many core hours something numerical that I want to do on a computer will take. Probably many of you have heard of Moore's Law, which was just the observation dating to the 1960s, I believe, that the number of transistors on the CPU doubles roughly every 18 months. And people have kept predicting that we're reaching the limits of that technology and the end is at hand. And so far it hasn't happened. Maybe it will come upon us. In the early days, what that meant was if I wanted my code to run faster, I needed to buy a newer computer, and it would, for instance, have a higher clock rate, and it would execute the same instructions, and they would just be faster because I had more transistors and it did each thing in the order I did it, and it made it faster. But that hasn't been true for a while. So for roughly 2 to 3 decades, how processors improve their performance, even though they're putting more transistors. If you were to actually go and look at how many gigahertz is the clock speed of my CPU, it's not necessarily that different now than it was 20 years ago. Instead, the way that these extra transistors have been utilized is to create some more sophisticated things that the CPU will try and do, which normally as a scientific programmer, you don't pay much attention to. I will talk about several of them, but the most basic one is what's called vectorization. So when I perform some computation, the most basic thing, if I add 2 numbers, is I add them and I get the result and I store the result because that's what I wanted. And if I have a whole bunch of numbers to add, then I just go through one by one and do that. And if my computer were faster, I would add them faster. But what modern computers do, and so I've just tried to write some pseudocode to illustrate it, is if you have several numbers you're going to add, let me put them all together in one register, and one operation will add, in this case, I've shown 2. I'll add both of the first elements of B and C to get A and the next ones. And now I get 2 things done in the same time that it would take me to do 1. As hardware has evolved, this number, the vectorization, has changed. So the earliest things would allow me to do 2 floating point computations, single precision, then 4, then 8, and now 16. Now, you're not going to find, unless you're going to a computing museum, something that has the 2 single precision, and you might still find 4, but you have several of these in play at once. That's not the only thing that's going on. There are also things that the CPU will try and figure out what you're going to do next, and if it's waiting for the input, it will reorder things in the order, and it will go ahead and execute some things if you're waiting on a conditional statement, and then have the answer ready, unless your conditional statement evaluates. So a conditional statement is if this is true, I'm going to do that. Is to turned out the other way, then it wasted all that time doing a predicted computation and has to walk all that back and do the right thing. You don't code this. Even if you write a compiler, you don't code this. The CPU itself is making this decision. So you've probably never seen this when you're working on code. But you need to be aware of it, because one of the takeaways is if I have a lot of if-then statements in my code, that may be hard for some of these modern computers to take advantage of. Even if I know about this, and there are places, for instance, in our analysis code where we've used this, you have to keep up with several different versions of vectorization. So this is why earlier I was making a point of saying that the nice thing about high throughput computing is I can run in all these different places in the world. But that's also a complexity when it comes that I want to care about getting the maximum performance out of my code, because the only way I have to prepare for many different kinds of computers that I might be running on. Now, in an ideal world, you wouldn't need to worry about any of this. You will write your C code if you have to write C code, or maybe you prefer to write Python or Mathematica or something higher level. And other people have written software called a compiler that will make that work efficiently for you. But in practice, for our scientific codes, that's rarely sufficient for the things that dominate our cost. So some of these other things that I've mentioned, and I won't repeat now since I just talked about them, but all of this is something that in software engineering parlance, if you're trying to get the most performance from your hardware, you have to have in mind. And the complexity is I can't just make one assumption about where I'm going to land. I have to plan for all possibilities. And if you don't, then you can see pretty large, you bought your shiny new CPU and they said it gets this many gigaflops, and you can get a tenth of that or even less in reality if you don't utilize these vectorized observations directly or indirectly. Now, none of that is to say that I think all of our gravitational wave scientists should be writing this vectorized code. I said I and a couple others have done it. It's almost at the level of writing assembly level code. When I was a teacher and would teach some computational courses, as a student, I want you to implement an algorithm I've described. So we'll do something about integrating in a differential equation, and maybe we'll do Euler's method, and I want you to write that code and do it. In reality, you should never do that. You should not be rewriting something that many, many people have written because they have written it better than you and they have worried about all of this. And so technically how this is implemented, and you may have seen this, is just using libraries that are designed to be high performance. And it involves thinking about my algorithm in such a way that I can break down the pieces that will take the most time into these common things that many other people do. So they're not just things that gravitational wave data analysts do, but they're things other digital signal processors want to do. They're things that people who are simulating partial differential equations want to do. And so this covers a lot of common scientific operations. My example is if I want to solve a system of linear equations, I don't open up my linear algebra book and start implementing some particular method there. There's a library of routines called LPACK, which has been around since I think at least the 1970s. Its reference implementation is in Fortran, to give you some idea of its age. And it calls another library itself called the Basic Linear Algebra Subroutine, which does all of the heavy lifting. And so all I need to do is not kind of hand code a loop where I'm just trying to do something the compiler won't figure out. I should be calling these libraries. And so if I do that, it will be efficient and it will land on each machine and do the right thing. But why I'm going into all this level of detail, it will worry about how many different floating point operations can I do at once? How do I need to access memory in an efficient way? Some of these out of order things, not having if-then statements that I can avoid. How do they do that? Well, they use a technique in which basically at the beginning of my computation, I look to see what sort of CPU I am, and somewhere I've written every version of this or every version within a set, and I pick the best one. Now, if you've never thought that you had to worry about this, the reason is because Intel and AMD and NVIDIA are very wealthy corporations, and they can hire a lot of software engineers, and they've done that. Right? So the reference libraries generally come from hardware vendors. They sometimes license them for a fee. They're usually not very much because their business model is we would like to sell you a CPU. So for you to get the best performance of your CPU, we'll make sure that linear algebra and FFTs and things like that are efficiently implemented. There are also some dedicated scientific computing groups that will do similar things. For those of you working in machine learning, some of those operations some of them will use BLAST and some of the things, but there are some critical computations that are different, but it's a similar approach. Somewhere, Alphabet, a parent company of Google, or Facebook for TensorFlow, Facebook for PyTorch, is paying a staff of engineers to do this kind of thing for you. I mean, I've looked at some of the internals of PyTorch while working on some gravitational wave things. So this works really well as long as my core operation is something that lots of other people need to use and where there's a natural market, as it were, for these sorts of computations. So the FFTs that I've mentioned, linear algebra, a lot of our things can be built out of that. And in that case, you don't really need to worry about all that stuff that I just spent a while telling you about. The primary place the model breaks down is when what you need to do that takes a lot of your time. Now, often you can have something, we always have something unique about our calculation. We're not just solving linear systems because our teacher asked us to, is where some part of my computation is both computationally expensive and it's something that nobody else but me cares about. So then if I want to be efficient, then I'm going to have to worry about some of this some way myself. And the software engineering term for this is domain specificity. So it's something that's unique enough that you're not going to find an existing library yourself. And I'm coming back to what I was saying about waveform modeling, that in practice, many of our waveform models, so I'm not talking here about the numerical relativity simulations themselves, although they will also have some domain specificity to them, but actually they'll use some partial differential equation solvers as well. But I'm more talking about what we have to do when we're doing sampling techniques. If I want to move around, the dominant cost of that is generating, what is this waveform? Oh, hit the wrong thing. Get back. Generating this waveform down here. And that's an evolving set of experts, some of whom are here, many of whom were recently here, who work on incorporating that. And typically this far, it's been written in either C or Python, but that is very domain specific. Intel doesn't have a set of engineers who are writing waveform models for us because they don't really care. to be honest. There's not enough other people who would use that. They're not going to be able to sell that to people who are buying their hardware in general. So what do we do about that? I want to emphasize that we have these differing areas of expertise, and neither of them is wrong. They're both needed. So waveform modeling itself is fairly sophisticated and combines some different things. At some point, you need the input from numerical relativity. So you need the experts who have written those codes and run those simulations. You also need analytical relativity for the early part of the waveforms and some data analysis expertise and physical models to stitch those things together. There are a few different families of waveforms that do this in different ways that are widely used right now. They may evolve differently into the future. But doing that is not necessarily, and in general, is not the same thing as the stuff I've just been talking about, all this low-level computing stuff. At the same time, in practice, as we've done our analyses in 01 and 02 and 03, and looking forward already to 04, these experts who come up with these models are always needing to incorporate new physics. I need a higher order analytical model. I need to update how I reference numerical relativity simulations. And I was just showing you that in 3G, there may need to be quite large gaps in improvement in the precision of those models. It's already the case that almost by the time that someone who does do this software stuff for a living comes along and tries to optimize it, we've moved on. And there's a new waveform that's the new best thing. There's been some attempts to do this, and in each Cardiff that I know they did this at one point, and kind of by the time it all got done, it was almost obsolete. So what's the model here? And we're coming here to the end of what I was going to say. The models are changing often, but that's not a thing we can criticize. That's the analysts doing what they're supposed to do. So we have to plan for that. The hardware capabilities are also evolving. I've mostly talked about CPU stuff. You're probably aware of GPUs and the best performance for these models. You really need to generate the waveform itself on the graphic processing unit. That's involving writing a whole different set of code. But these implementations need to be maintainable. So we now refer to, I think, what we call the lottery factor instead of the bus factor of we don't need there to be one person who writes this almost assembly level language code, because then that individual is forever responsible for maintaining. It can be difficult to maintain. There are some wrappers that can help with some of this. I've mentioned a couple of these. The first one, for instance, is what Facebook uses internally in PyTorch for doing this. But the existing frameworks, some of you will be familiar with last week, make this difficult to implement. So what's been done so far in the analysis codes we've done is just let me write all this in this very low level way, and then it becomes obsolete very quickly. It's proven challenging to directly do this and maintain it. So I'm advocating for, as we look to 3G, focusing the effort required to build the pieces. So an example of this might be in the phenom waveform family, where I'm using the spheroidal harmonic decomposition. I need to sort of write each of those in a way that builds on lower functions, but where I can then plug that in and have something automated that can convert that. So I write one thing that's more human readable and generate all the different versions that I've said that we need for this. As an example, even if I do something basic like e to the I theta, now, as you probably know, we do a lot of that, and that's what I want to do if I just want to. I've generated a waveform, and I just want to shift it in time, which I want to do if I'm comparing the time shift from one detector to another. It's an order of magnitude difference if you just take the C implementation that you get from GCC, what it is, versus if you do this carefully. In some cases, a factor of 25 I've seen, and that was not on the newest hardware. I won't go into this detail because I think I'm running short on time, but you also then have to think about how I integrate this with the code that's going to use it. And if I'm doing sampling in particular, or maybe if I'm doing something else for machine learning, you don't want to generate the whole thing and then come along and add up multiply by your data and add that up for hardware memory access reasons. You can be surprised that sometimes reading my memory from RAM can be slower than hundreds of operations on my CPU. So you want to generate it, add it, and keep a running total. So there are these places where you need to do the software engineering. I've sort of said that we're working on this, and we are, but for 3G, one of the things that I think is a little bit present in the GWIC report, but not as present as I'd like to see in some of the other reports, is a recognition of this. There are different places you can imagine this happening. It's not always exactly in the typical remit of an observatory. It's not what you need in order to produce calibrated strain data. If you expect it to just exist in scientific computing, I'm trying to advocate for saying often those expertises don't overlap. And in practice, we're not finding people who do that. If you have never read this paper, it only exists in the archive, as far as I know, called the AstroPy problem. It's by AstroPy developers. So the problem that they're talking about is who maintains AstroPy and who gets rewarded and funded for doing that. Everyone uses it, but there's like one paper with 400 citations, which is really not, this is a 2016 paper, it's probably, that's really not representative of how widely used AstroPy is in astronomy. And the focus of this paper is they're saying, well, who goes to the trouble of having this well-maintained software? And so we're going to have some cooperation between domain experts and software engineers. And mostly as we're looking for 3G, we need to sort of plan for this. So thank you for your time.